Can you truly cross a room? It sounds like the simplest thing in the world. But more than 2,000 years ago, a paradox suggested something shocking. Maybe motion itself makes no sense. Imagine you want to walk from one side of a room to the other. Before you reach the end, you must first reach the halfway point. But before you reach halfway, you must reach half of that distance. And before that, half again. And before that, half again. The path seems to break into infinitely many smaller steps. So Zeno asked, if there are infinitely many steps to complete, how can you ever arrive? Of course, in real life, you do cross the room. But Zeno's paradox revealed a deep problem. How can finite motion be built from infinitely many parts? This question haunted mathematics for centuries. People could see arrows flying, rivers flowing, planets moving, and shadows changing. But describing continuous change with perfect precision was incredibly difficult. Calculus was born from this mystery. It is the mathematics of change, motion, curves, accumulation, and infinity. But calculus was not discovered in one place, by one person, in one moment. It was built slowly, across cultures and centuries. One of the earliest great chapters begins in southern India, with the Kerala school of mathematics. Around the 14th century, a brilliant mathematician named Madhava of Sangamagrama explored infinite processes. Madhava studied circles, curves, and trigonometric functions. He discovered infinite series, ways of adding smaller and smaller terms to calculate useful quantities. This was a revolutionary idea. Infinity was no longer only a philosophical puzzle. It could become a method of calculation. Madhava showed that by adding infinitely many shrinking pieces, mathematics could reach finite and accurate answers. In a way, this was already touching the heart of calculus. Centuries later, in 17th century Europe, science was changing rapidly. Astronomers were tracking planets. Physicists were studying falling bodies. The old mathematics was no longer enough. In England, Isaac Newton developed his version of calculus while thinking about motion and gravity. For Newton, quantities were not frozen. They flowed through time. He studied how position changes into velocity and how velocity changes into acceleration. Calculus became the language of motion. With this language, Newton connected the falling of objects on Earth with the movement of the moon and planets. The same mathematics described both the apple and the heavens. At nearly the same time, in Germany, Gottfried Wilhelm Leibniz developed his own version of calculus. His approach focused less on physical motion and more on symbolic structure. Leibniz created a powerful notation for tiny changes and accumulated sums. His symbols were so clear and flexible that much of modern calculus still uses his style. Newton gave calculus a deep connection to physics. Leibniz gave calculus a beautiful symbolic language. Together, their ideas transformed mathematics forever. Calculus gave humanity two great tools. One tool measures how fast something changes at a single instant. The other adds infinitely many tiny pieces to find a whole. These tools worked astonishingly well. They helped explain motion, gravity, curves, areas, planets, machines, fluids, electricity, and eventually modern technology. But there was still a problem. Early calculus was powerful, but its foundations were not completely clear. Mathematicians asked, what exactly is an infinitely small quantity? What does it mean for a value to approach another value? Can infinity be handled with complete logical precision? In the 19th century, Bernard Bolzano helped push mathematics toward rigor. He emphasized careful definitions of continuity, limits, and logical proof. Then Carl Weierstrass helped rebuild calculus on a solid foundation. Instead of relying on vague ideas of infinitely small quantities, he gave precise definitions based on limits. With Bolzano and Weierstrass, calculus became modern analysis. The mathematics of motion became a disciplined theory of limits, derivatives, integrals, continuity, and infinite series. And now, Zeno's old paradox could be answered more clearly. An infinite number of smaller and smaller steps can still add up to a finite distance, completed in a finite time. The mystery was not that motion is impossible. The mystery was that infinity needed a new kind of mathematics. From Madhava's infinite series, to Newton's physics, to Leibniz's notation, to Bolzano and Weierstrass's rigor, calculus was never just one discovery. It was a long human journey toward understanding change itself. Today, calculus shapes physics, engineering, biology, economics, machine learning, and almost every science of motion and growth. And it all begins with one astonishing idea. To understand the universe, study the infinitely small.